Hi, and welcome back. Where we left off was I gave you a matrix A, 1, 2, 4, 7, and I asked you to find the inverse of the matrix. Now this question is really just, can you apply the formula in the theorem? So I'm just applying the formula. The inverse of A is 1 over 1 times 7 minus 4 times 2, and then I'm switching the order of the values on the diagonal and switching the signs of the antidiagonal. So let's just clean this up here. So this fraction becomes 1 over negative 1, 7 minus 2 minus 4 and 1. So this means I have to multiply through each entry by negative 1. So the inverse should be minus 7, 2, 4, negative 1. Now the nice thing about looking for the inverse of a matrix is that you always have a way to check your answer. Right? And to see why you have a way to check the answer, what we're claiming is we found a matrix such that when I multiply by the original matrix, I should get the identity. So you can always just check your answer by multiplying back out. So if I take my matrix 1, 2, 4, 7, and I multiply it with my proposed answer, and what I should get is the identity matrix of size 2. And notice that I have 1 times negative 7 plus 2 times 4, so that will give me 1. I have 1 times 2 plus 2 times negative 1, which gives me a 0. And then I carry on and work out all the details and I get the identity. So I'm very happy. I'm going to give myself a happy face for getting the answer correct. And you too will get a correct answer because you will always be checking your work. Now there's a nice collection of properties that an inverse will have, and they're kind of listed in this statement right here. So I'll fill in some of the missing steps here, and we'll look at a proof for statement 4 and 5. Okay, so let's quickly go through what the statement is saying. It's saying that if you already know that the matrix A and B are invertible, then the inverse of your matrix is also invertible, where the inverse of your matrix the inverse of your matrix is the matrix A that you started with. Also, we get that the transpose of the matrix is invertible, where the inverse of the transpose is the same thing as taking the inverse of your original matrix and then transposing that matrix right there. I've already written what happens if we multiply a matrix by a constant. So if you take a matrix that's invertible, you multiply its constant, you don't destroy the invertibility property, it's still invertible, and the inverse of your new matrix is the inverse of your C, because C is a real number, you can find its inverse, and multiply it by the inverse of your matrix A. Now the product of your two matrices, because they're invertible, the product of them is also invertible, but you have to pay a lot of attention here about what the inverse of A times B is, and the inverse of it is equal to B inverse times A inverse. So when you're bringing in the inverse sign and bringing it inside of the brackets, you actually switch the order. So pay attention to that. And the other property that you have about inverses is that it's unique. So if A has an inverse, you will only find one matrix that allows you to find the inverse. It won't be the case that A has two different inverses. So let me just show you why 4 and 5 are true. Okay. So we want to show that A times B is an invertible matrix. So we need to find some sort of matrix C with this property that A times B times C is equal to the identity. And similarly, we have to show it on the other side, that C times A times B works. And the claim is that the matrix B inverse A inverse works. This matrix works. We're just trying to find an inverse, so we just need to find one matrix that works. And now notice that this matrix here exists because B inverse exists and A inverse exists, so we can definitely multiply them together. So we're going to just check A times B inverse A inverse. Now, multiplication is associative, so we can regroup the parentheses. So this is the same thing as A times B inverse times A inverse. This part inside is just the identity matrix. And A times the identity matrix is just A, and then A times its inverse is equal to the identity. And then if we do this on the other side, we get the exact same thing. We have B inverse A inverse times A times B. We're going to squash the A inverse and the A together, as we do it right here. And once these two are pushed together, they become the identity. Identity times B is just B, and this gives you your identity. Sometimes this is called the sock and shoe property. So think about this. Think about matrix B as first putting on your socks, and then you're putting on your shoes. But now you want to reverse that process. Well, how do you reverse the process? Well, you first have to take off your shoes, and then you have to take off your socks. So that's why it's sometimes called the socks and shoe property. You have to kind of reverse the order in which you do those two things. Okay, what about the last claim here is that the inverses are unique? Well, here's a kind of a standard proof exhibiting the uniqueness of an element. Suppose that we had inverses of the matrix A. So that means that A times B is equal to the identity, and B prime times A is also equal to the identity. Okay. But then we can multiply both sides of one of these matrices by the other one. Okay, so let me make it a little bit more clear here. But then B prime times AB is equal to B prime. I'm just taking this expression right here and multiplying both sides. Oh, maybe I'll make this a little bit clearer. I'm multiplying both sides on the left by B prime. So we can rearrange this. On the left-hand side, let's regroup our parentheses. And on the right-hand side, this just becomes B prime. Now, what do we know about B prime A? Well, that's equal to the identity. But the identity times B is equal to B, so we get that B is equal to B prime. So if we had two matrices that are acting like the inverse, then this argument here shows that those two matrices that you started with are actually the same. And so this shows us that every matrix, if it has an inverse, has to have a unique inverse. Okay, so we'll take a short break here. In the next part of the lecture, I'll give you a procedure to find the inverse of any n by n matrix, provided that this inverse exists.